So we already learned about polynomials and factoring and all that kind of stuff. We're going to use some of those same skills here in this 13.4. We're going to talk about domain. We already talked about domain a little bit with parent functions. But look at what they're asking you to do here. Use test point, and that probably should say a test point or test points, to determine when this thing is greater than or equal to 0. Now here's the beautiful part about this. It's already factored for you, the top and the bottom. Sometimes you might have to do that on your own, but let's just go with this. So just ignoring the bottom and ignoring the fact that this says greater than, let's just start with where does this thing equal 0? So look at the top. If you set each of these things equal to 0, and I stop writing all over the page, we would get x equals 0, and if you set x plus 6 equal to 0, then what would x itself equal? -6. Okay, so these are 2 points that make the whole thing 0, right? Because if the top is 0, then the whole thing is 0. So here's what I want to do over here. Start this number line, and we're going to go ahead and put -6 over here, and we're going to put 0 over here. We got to put them in order. All right, now, is -6 a valid answer? What happens when I plug -6 in for x? It makes the top 0, and is 0 greater than or equal to 0? Yes. Okay, so I'm going to put in a little closed circle right here for both of these numbers. They are answers. And I'm going to actually have a whole interval of answers. But -6 and 0 are answers. Let's just pretend for a second, though, that or equal to was not there. Then I would put open circles here. Okay, if I only wanted to know when the thing was positive and not or equal to 0, that would be a different problem. Okay, so now let's think about the denominator. All right, what happens when we set x minus 2 equal to 0? Then x equals 2. I know some of you are a little freaked out by the process, but I'm just setting everything equal to 0 and solving for x. Okay, now let's put these two numbers also on the number line. So we got to think, where would 2 go? It would go over here to the right of 0. -2 would go in here somewhere. It does not need to be completely accurate, like the spacing. It does need to be, though, like in the right order. Okay, so let's think about, is -2 and 2, are they solutions or are they just boundary points? What happens when you say plug in 2? You get 0 where? You get 0 on the bottom. And this is something that's really huge in calculus. A number divided by 0 is not 0. It is undefined. So we got to think, does plugging in 2 make the left side greater than or equal to 0? It does not. So we're going to put an open circle. These are going to act as boundary points, but they're not actual solutions. And the next thing we're going to have to do is figure out, okay, where could I shade on this number line? Where are my solutions? Where's not my solutions? And this is where the whole test point thing comes into play. So way off here, let's go ahead and put a little negative infinity. And over here, let's put a positive infinity. And let's take a number between negative infinity and -7. Anybody got an idea? -8. Sure. So I'm going to do this, but I'm going to erase what I'm about to do. So you may want to erase, or you may want to leave yourself room or use your pencil or however. Okay, let's test x equals -8. All right, so if we test x equals -8 and we plug it in right here, we're not going to actually evaluate a number. We're just going to figure out if this thing is greater than or equal to 0 or is it not. So if I plugged in -8 in for x, I would have a negative. What about negative 8 plus 6? Would that be positive or negative? Negative. And what does negative times negative make? Positive. So I'm going to do this. And I'm going to erase this stuff in a minute because we're going to have to test another point. So the top is positive when x is negative 8. And that's going to be true for any number we would have picked over here. So let's look at the bottom. What about negative 8 minus 2? That's going to be negative. And negative 8 plus 2, that's also negative. And a negative times a negative is a positive. So what is a positive divided by a positive? A positive, and is that greater than or equal to 0? Yes. So we shade this in. Now this is the first time you're seeing this. So is it weird? Yes. We're going to keep going over it. The guaranteed way of you not learning this is by checking out because you don't like this. You got to stay with me here. So now we're going to test something else. Okay, so this is what I was saying. I'm going to erase this and we're going to test something else. We're going to test a number in between negative 6 and negative 2. It doesn't matter which number. I'm going to test negative 4. You can, if you want to just see if you get the same results, you can test negative 3. So again, we plug negative 4 in for x. I get a negative. What about negative 4 plus 6 though? That's a positive. And what is a negative times a positive? A negative. Okay, so the top is a negative. And now we do the same thing with the bottom. Negative 4 minus 2, that's a negative. Negative 4 plus 2, that's also a negative. And a negative times a negative is a positive. So think about this. What is a negative divided by a positive? It's a negative. So would that thing be greater than or equal to 0? No. So don't shade here. The numbers between negative 6 and 2 are not my answers. They will not make this a true statement. And we keep going. Eventually it's going to get a little bit easier because you're going to deal with positive numbers. So we could have started at the right and moved left, but so now we could test, say, negative 1. If you plug negative 1 in for x, you get a negative. Negative 1 plus 6. That's positive. Negative times a positive, that's a negative. Okay, negative 1 minus 2. That's a negative. What about negative 1 plus 2, though? That's a positive. Negative times a positive, that's a negative. And a negative divided by a negative is a big fat positive, which is greater than or equal to 0. So these numbers right here work. And I picked negative 1, but you could have picked, if you wanted to get real weird, you could have picked like negative 1/3. You would have gotten the same result as me. Now, what have you noticed so far about the pattern of shaded and not? It kind of alternates. So if we had to just use that pattern, which I'm going to tell you does not always hold, but it will a lot of times, what would you guess with if we tested something in here? You think it's not going to work. Okay, so let's test that. Let's test a number between 0 and 2, like a 1, positive 1. So that's going to give me a positive. 1 plus 6, that's also positive. So the top is all positive. 1 minus 2, that's a negative. 1 plus 2, that's a positive. So the total result is positive or negative? Negative, which is not greater than or equal to 0. So we do not shade. It's like a test. Did it pass or fail? In this case, it failed. And if you had to guess, what would you guess for after 2? Shade it. So it's kind of a tedious process, but it's really not that hard if you just buckle down and do it. So if we plug in something like 3, everything's going to be positive. So that's what I'm saying. Some of the ones on the right are easier, which is greater than or equal to 0. Different ones than I did? You would have gotten the same result. As far as positive and negative concerns, it doesn't matter if you test 3. As long as you test anything between 2 and infinity, you're going to get the same result. So how do we write our final answer? You take what's shaded and you write it in interval notation. Now, infinities are always parentheses. You can't equal infinity. Then we get to -6. Okay, was -6 an actual solution, or was it just acting as a boundary? How do we, well, sorry, I just kind of gave this away. We show that with a bracket versus a parenthesis. Okay, so look how I'm going to do this. And if this is where we use union. We talked about this with domain and range. We'd skip all of this right here. And see how the -2 is just acting as a boundary? It is not a solution, so you'd put parentheses there. And then again, bracket with the 0. So you guys are going to be your own worst enemy with this. I know the conversation students have with themselves. It's either I can't do this or I don't want to do this. Okay? To be honest with you, you got to just like overcome that. This is kind of just one of those things. It's really not that bad if you just buckle down and do it. Okay, so that was a pretty lengthy example. And honestly, we start with that because you get to do a lot of test points there, so it makes you understand the process. So then we get to something like example 2, which, by the way, we've already done a problem like this semester. Okay, but maybe we can use this idea of test points to make it a little bit easier. So what do you know about domain and what you can and can't do with numbers? Okay, here's the deal. I can't talk to myself, so I'm just going to keep going, and I'm going to move really fast. This thing right here has to be positive. Positive because you don't want to divide by 0 and you want to square root by a positive number. Now, if you can factor this, which I'm not going over in this lesson, you get something like this. X plus 2, x minus 1. So what are my solutions for x? -2 and 1. This was already factored for us in example 1. Now we had to do this. So we put them on a number line, negative infinity down here, infinity down here, and we test. Okay, if you plug in a number that's between negative infinity and -2, this is actually easier to test than the one we did. You can test either here or here. You're going to get a positive result. So is greater than 0 positive? Yes. Okay, we are just going to use boundary though for -2 because the or equal to is not there. Now using the pattern from before, probably it's going to alternate shade, not shade, shade. But you could just test to 0. 0 squared plus 0 minus 2, that is not greater than 0, so then you wouldn't shade. And if you test a number larger than 1, you'd get something like this. So that's how you write your answer. This is how you use this idea of test points. So see how there's no or equal to? Or equal to would denote a closed circle. Just a greater than or less than would be an open circle, therefore parentheses. Oh. It's just a strategy. It's just a strategy for you to solve inequalities. All right, let's look at the next one, and then we're probably going to run out of time. So there may be an extra video you guys get to watch tomorrow. Sometimes it goes, there's weird behavior. Okay, you'll learn more about why that happens in calculus. Okay, let's talk about long division, everybody's favorite. You take the bottom and you divide it into the top. Now remember, just like with synthetic, if you have any terms missing, you need to put a placeholder there. So we haven't done this in the last weeks, but you've done this semester. So here we go. X squared goes into x cubed. How many times? 1 is kind of the first way to answer this, but remember what we got to go. Something times x squared is x cubed. X. So then we multiply. X cubed plus x squared minus 2x. And then we subtract. Yeah, I just flipped all the signs. We subtract, so all the signs change. So here you would have 0 minus 1. That's going to be negative 1 x squared. And then negative x plus 2x, that's positive 1x. And then you bring down plus 3. And then you go again. So now we divide. X squared goes into negative 1x squared. Minus 1 time. Negative 1 times x squared is negative 1x squared. Negative 1 times x is negative 1x. Negative 1 times 2 is positive 2. And then when you switch all these signs, then you can figure out your remainder. Okay, so here, okay, just to finish this one up, your remainder here would be 1 because of positive 3 minus 2. And so the way we would write our answer is we'd write what we got plus your remainder, 2x plus 1, over your original denominator. That's probably the easiest way to explain that. If you don't have a remainder, your remainder is 0, then we would have just left it at x minus 1. Okay, you've seen stuff like this even since Algebra 1. They're going to tell you which letter to get by itself. And that means that A has to be by itself, and it can only be on one side. Bunch of fractions here, though. So what you would want to do is find out, take all the denominators and multiply both sides by A, B, and C. So think about it this way. If A, B, C gets multiplied to 1 over B, the B's are going to cancel, and you're going to be left with just an A and just a C. So how would that apply to this other side with 1 over A? The A's would cancel, and you would be left with just B times C. What would you have for the third piece? You'd be left with A and B. Now remember, you're trying to get A by itself, and it's in 2 places, and we don't want it in 2 places. We want it in only 1 place. So the first thing is get them on the same side. Now this is not going to cancel, so let's just kind of rewrite what we have. It's not going to cancel, but I can factor out the A because they both have it. Just like if this was a number. And if you factor out the A from AC, you're left with C. And if you factor out the A from AB, you're left with B. So this is kind of weird because there's really no numbers in here. But you're doing the same thing if you had numbers. Okay? So what's the last thing you need to do to get A by itself? Divide by C minus B. And you know you did a good job here, that you're done, when whatever you're solving for, in this case A, is the only A left. So see how it's only B's and C's over here. So that's that answer. Okay, let's look at example 5. This gets back into rationals. Okay, so if you look at where the hole is, okay, remember from Rady, okay, or Frady, and if you wanted to kind of go back, this would be, oh goodness, I can't remember it off the top of my head. Chapter 8 or 9. Anyway, sorry, a little frazzled there for a second. You know that you get a whole, like if you have a fraction, from a term that cancels top and bottom. So what you want to do here is you want this thing to equal 0. So think about, you would add 2 over. You could say switch the sign. So there's an x plus 2 that goes on the top and an x plus 2 that goes on the bottom. All right. Vertical asymptotes, though, are just the denominator. So if x equals 2 is a vertical asymptote, then x minus 2 goes on the bottom. And what else would go on the bottom? If x equals 3, you'd write x minus 3. Okay, because if you set these things equal to 0, you would get those values. Okay, x-intercepts, that goes on the top. So if you think about it this way, this is the bottom, this is the top, and the whole is both, top and bottom. All right, so if x equals 5 is an x-intercept, then x minus 5 goes on the top. Also, an x minus 1 would go on the top. Now we're almost done. I'm going to even change colors here. This whole thing right here is that rhyme. The degrees are the same, so we play the coefficient game. So we want this 2 to be like 2 over 1. So we put a 2 over 1, and there's your expression. So if we're doing something like 6, where we're given the expression, the first thing I want to do is factor it. Right? Again, I'm not going to go over this factoring thing. If you don't understand factoring, you've got to come in for tutoring. All right, x plus 1, x minus 3, x minus 1, x plus 1. And the first thing you do is look for, is anything canceling? Yes, x plus 1 canceled. That means I do have a whole. If you set x plus 1 equal to 0, you would get x equals negative 1. And then how would you find the y value? Well, let's totally cancel that out. And let's plug in negative 1. Negative 1 minus 3 on top, negative 1 minus 1 on bottom. That would give us negative 4 over negative 2, which would give us 2. That's the whole. Okay, just like before, roots, that's x-intercepts. This is where you'd be looking at the top. So if you set x minus 3 equal to 0, you get x equals 3. Probably a better way to write this, though, would be to write the point 3 comma 0. And there's no multiplicity because it's not written twice or anything. The asymptote part you're going to put at the bottom. All right, and this would be x equals what? 1. And this is a line, so we don't write it as a point. Again, there's no multiplicity, so then there's no tangent or together. Don't worry too much about this in this unit. All right, in behavior, degrees are the same. Play the coefficient game. So y equals 1 over 1, which would be 1. Y-intercept, it's the last thing, but it's always the easiest thing. Just plug in 0. So 0 minus 3 over 0 minus 1, that would give us a positive 3. Okay, example 7. If you notice here, there's some repetition. And so I want to think back to how we did the ABC problem. We took the denominators and we multiplied both sides by those denominators. So we're going to multiply both sides by x and x plus 2. And when you multiply it here, just like the ABC problem, the x plus 2's would cancel and you'd be left with x times 2. Okay, what happens when we multiply here? The x's would cancel and you would have x plus 2 times 3. What would you get on the third side, or on the other side? The x plus 2's would cancel and you'd have an x, and then you'd be multiplying it here by a negative x. That's how you get rid of those fractions easily. Let's clean this up. 2x, let's distribute the 3, 3x plus 6. X times negative x would be negative x squared. This is now a quadratic. Okay, so I'm going to go through the rest of this even faster. Add that x squared over, add the 2x and the 3x to make 5x, and factor. This is not an inequality, so I do not need to do test points. You're good to just go ahead and solve. If it had been an inequality, then that's when you would do test points. Okay, last problem. The first thing we need to do is remember what f of g of x is. So let's take g of x and actually substitute it in. So I'm like literally f of, instead of writing g of x, go ahead and write in square root of 2x squared minus x minus 15. And then what is f of x? It's 1 over x. So what we're going to do here, instead of 1 over x, we're going to do 1 over this thing. 1 over this. So that's f of g of x. That's not really our final answer, but I'm going to box it just to make it clear. What we now need to do is the domain. This is kind of what we did in example 2. So we take this and we set it greater than 0, which means we got to factor and do test points and all of that. Okay, if you're watching this video, I'm going to encourage you to stop here, try this on your own, and then pick up and check your work. Okay, if you're following the video right now, then we need to factor. So this becomes 2x plus 5 and x minus 3. I'm not showing those steps. So if this was just an equal to, x would equal negative 5/2 and x would equal 3. Since we are doing an inequality, we can't stop there. We need to put it on a number line where negative infinity starts it and infinity stops it. And then we test. Since there's no or equal to here, these are boundaries, and then we just test each thing. And you can test it into this multiplied out, or you can test it into the factored form. So again, if you're watching this video, I'm going to encourage you to stop, try to test it, and see if you can write your answer. Okay, if you take a number over here and plug it in, you do end up getting a positive. Since that's greater than 0, we would shade here. If you try to plug in a 0, you would get 0 minus 15. That's not greater than 0, so don't shade here. And notice again that there's kind of an alternating thing. That doesn't always happen, but it does happen quite a bit. And then here's our answer. Okay, I know that last part was pretty quick, so if you need to go back and rewatch it, you can.